So, okay. I guess, Adam, then you can continue for the afternoon session.
Yes, I can start. So there is a question whether we should, let's say, we will try to provide all of the information that should be necessary to run the cases for this hands-on session. So yeah, you don't really need anything more than this, at least for this set of cases we are going to run. So I hope everybody already downloaded the code. To be honest, I'm not fully sure how would it go, because it's the first time when I'm doing this kind of stuff through the through Zoom. And if you don't have two screens, then probably it would be difficult to see both slides, me and to do something else. I don't know, but we'll have to somehow go through this. So I hope you already downloaded Nek. I hope you have GCC, Fortran, or whatever it is, C and Fortran compiler. You have some kind of MPI to visualize Visit or ParaView. And of course, you need as well gmake. And for the next use case, the first one you will not need it, but for the next one you will need as well gmesh. I hope everybody has already installed that. So the first example is example which you can find under the example directory. And actually, the only thing I would like to get through this is to show you how the whole workflow for producing and running a single case looks. So you have, your tar file, you have to extract it. And then what you have to do first, actually, is you have to compile your cases. So I will have to get out of the presentation right now to do the same. So I hope you can follow me as well on your own to see this. So I've already have the Nek5000, which is uncompressed tar. I'm here. That's my path. So what I have to do, I have to export Nek source root, and then I will need this. Oh no, it's different. It's grave to know where my code actually is. I could add this as well to the path. I usually don't do this, but you could do this. And then what we have to do, we actually have to compile the tools. You see here, there is a number of tools. We have this like CGNS, Exa2Nek, and gmesh to Nek. Those are the three converters. And then we have as well GenBox, which is the meshing for the simple box topology. And of course, GenMap. Those are the ones we are interested in. So to compile it, it's enough to run or make tools all, or make tools and the name of the tool we would like to compile. Like, for example, make tools GenMap. And then I'm building GenMap. Now it's done. GenBox. Now it's building GenBox. We will need as well gmesh to Nek. So now we have all those required tools for our test for today hands-on session compiled. We can go up to the bin directory and we can check if they are there. And we have gmesh to Nek. That's good. We have as well GenBox and GenMap. So that's what we needed. So, and I hope you can follow me as well with this. So now we go up. We have our run directory, which is completely empty, because that's the place where we will locate our setups. We have as well the examples directory. And from the examples, you see there's a number of different examples here. Right now, we will focus on this ADUV example. So what I simply do, I simply copy cp-r example ADUV to the run directory. And now I go to the run directory, to ADUV. And what I have here, I have size file. And that's, as we can see, it's a two-dimensional case, polynomial order 7. And this is a pn minus 2. The global number of elements is not bigger than 50. And the local number of elements is actually, no, let's say, no, not 5,500. It's actually equal to the global one. But that's okay. Those are 2D elements. That's fine. Usually, LELT is much smaller than LELG, because LELG can be of the order of million elements, sometimes up to million, 100,000. That would translate to a billion grid points, kind of. And of course, LELT cannot be bigger than, let's say, 100, 200, 300 in the three-dimensional case. That's usually, of course, it depends on the machine, but this LELT usually for us, for the three-dimensional case, is around 50 to 100. So that's the numbers which we usually use. So there is no need to change anything here. Okay. So we have as well here RIA, and we have as well here map file. I will remove the map file, ADUV map, because this actually we should generate here. But we have the ADUV user. And then we have all of those required routines. In the beginning, we have the exact solution, because actually that's what the example is it compares the exact solution, add a solution, with the simulation, so we can actually find the error. We have the properties, nothing happens. There is no forcing here. And then, of course, we have this user check, simulation, which the routine which I already mentioned, that's the place, because it's called after every time step. So that's the place when you interact with the solution. So you can extract some information. You can calculate the error in this case, and so on and so on and so on. So that's our main place to act. Now there is one thing which is actually interesting here. You have this if state. If state I step equals 0. I step is the number of the time step of our simulation, and it allows us to distinguish between the initialization and the time loop evolution. So if I step is equal 0, then we know we are in the initialization. And this line means that during the initialization, we actually want to outpost our initial condition, or our exact solution in this case, because we first calculate the exact solution, and then we write them to the disk. So we will not go much further here about this, what's there, because I will talk about this in the next, or maybe one of the next cases. But to compile, I have to run the make-Nek script, which is located in the bin. I know where it is, 2 directories up. And then it's simply make-Nek, ADUV, and enter. And you see that it starts with building a third-party libraries. And it will generate all the code which is necessary. And after that, it starts to generate all the core code. The interesting stuff for those who are not familiar with Fortran, you can find here a lot of warnings. Most of those warnings are related or to some arguments or to the size of the common blocks. And you don't have to worry about those. So now we have the compiled code. Nek5000 is the executable of Nek5000 should be here. Yes, we have it. So what we need a RIA file, which is an old type of the parameter and mesh included in one file. And that is why I was describing it during the presentation. And you see you have this long parameter section. Here we have the time step, which is negative meaning the constant. We have number of steps, and so on and so on. This is followed by the description of the mesh. And description of the mesh actually is very simple. You see, you have x and y. This is x, this is y coordinates of the first, of the second, third, and fourth vertex. So that's the mesh description. And what it means, there is missing information about the connectivity. This connectivity we have to generate simply by running located under bin genmap. And genmap will ask us for two things. Now, one is the name of the case, which is adduv, and then it's about the parameter, which usually I set on the level of 1%. This parameter is actually a radius of the small sphere which will be generated along every single vertex. Connectivity finding is based on the very single algorithm where you calculate the biggest diagonal of your element, then you multiply this by the parameter which you provide to the genmap. Then every single vertex is surrounded by the sphere, and simply you perform a search through all of the vertices of the whole domain, all of those elements, and you see how many of those vertices simply pop out inside the sphere. And all those vertices are counted at the end as one. And that is why when you look into this adduv map file, which for this old version of the code is a text file, what you can see that actually it's simply 5 columns. And when you look into those second, third, fourth, and fifth one, you see that some numbers are repeating. They repeat because simply those are the global numbers of the vertices. The first column contains the information about partitioning. And that's enough for Nek5000 to create proper QQT communication algorithm, because that's what it only needs, the information who is sharing vertices and faces and edges. And as well to provide global partitioning in that case. And of course, the next step would be to run the code. Once again, from bin, I run nekbmpi. Nekbmpi is simply a parallel script. It's a very simple Gmesh. B means that the output will be moved to the file. And then we simply put what is the name of our case, because the runtime parameters has to be read during the initialization, and how many processors. Let's say 4. And what we can see right now is that the first stuff which was created is this session name. Session name simply contains 2 lines. It's the name of the setup and the directory where the case is run. Then you have the log file, which actually is, if you would look later, this log file is just a link to the adduv log dot and then the number of MPI runs we're running this. So we have eduv dot log4, and there we have all of the log files. I will not go through all of the information which is contained here. I will just show you that every step ends with those error information. So what it contains simply is the information, what is the error, what is the simulation time, because here you see step, simulation time, and error. Error according to X, error according to Y, and pressure. And that's actually the effect of our action inside user check. The whole idea behind this case is to see how exact our solution is compared to the analytical value, analytical solution. So we can actually, from the log file, extract all those error lines. So we simply do grep error log file to some error text. And we can have this error. Okay, it's text in my case. And we could extract every action from which was performed after every step. And we see during initialization, we have some given error. And then after each step, we provided this output. And we can simply visualize that. GNU plot, and this is this error text using second versus third. And okay, it doesn't show much here because the pressure error during the first step is rather high. So what I have to do, okay, I will change the upper. So this is the X, this is Y, and let's put it to 0.0001. I guess that should be enough. Yes, that's enough. So the plot looks following. Okay, I probably have to replot it. We have 3 lines. Two of them are the velocity, X and Y, and they go from 0 because the initial condition was the exact solution. However, the pressure has initially very high value, the error, because the initial pressure was 0 everywhere. So you have to wait a while until the pressure will go down, and then they will keep some value which is related to the tolerances which we defined. Okay, so that would be this. Now we can go back to the presentation. Was it too fast? Was it fine? Have you managed to run the case? Or should we repeat something about this? It was just about showing the general steps, what you have to generate, that you have the mesh in the real file. Okay, a bit fast. Yeah, is there something we should repeat or? Okay, maybe we should, Philip, what do you think? Should we start with microphone on or?
Maybe now we can just wait for five minutes, or I mean,
okay.
wait for 5 minutes.
You see exactly, let's see what I've done to get the output. I think it is in the next slides. It's here. I first grabbed error because, you know, we can go back. I can go back here.
I think the main question now is the GNU plot. Yeah, exactly this. Because
okay.
I think GNU plot is, in this example, is the most difficult bit.
Okay, I'm used to GNU plot. I don't know what about, you know, it's whatever, you know, after you generate, you extract those error information from the log file. Then you can use any file, because you see that the error txt. It simply contains the step number, time, and the error for the given variable. And this is x, y, and p. So x velocity, y velocity, and pressure. And you see from the beginning that initial x and y errors were very small. Initial pressure error was very big because the pressure was 0 everywhere. Pressure is not initialized. So you can use any software to simply plot second versus third line, third column. Yeah. Okay, so maybe I will as well add one more step, because right now what we have, I'm sorry, we have the log file, we have the error message, which we extracted, and we have a number of the plot files. So to visualize this, we need a metadata file, which simply will provide information for visit or for paraview. Visit and paraview use exactly the same metadata file. So what we have to do, we have to generate this. But what's important, we have a session name file. And this session name file contains the information about what is the name of our setup. So using this session name, because if it exists here, we can use a script which is done visnek. We simply run bin visnek, and this run business visnek generated ADUV Nek5000. Well, we can look what is there. So what we have here, we have simply a name, and you see it's a C-type formatting, that you have 1 digit, 5 digits. We have the name of the file. Then we have the first step and how many files we have. And with these files, you could simply open visit or paraview, and inside the visit or paraview, you could open this ADUV file to visualize that. I could actually run it right now. I can run visit 3.1. It will take a while. And then I simply can open the file. Okay, now we have the window of visit. I'm running my stuff on the cluster. So when I open the file, I have to change to the cluster. It's Stuxnet. And then I have to go to the path. So go back to visit. Inside visit, I open the new generated metadata file, which is called ADUV Nek5000. I open it. Okay, I should visualize this in parallel. And then I simply can visualize. Let's start with the mesh. So we can visualize the mesh. And that was very simple box structured mesh. And then I can simply hide it. I can start to look into the velocity components, and I can see how they evolve. Okay, so is this case clear? Because what is the main goal of this case is to show the whole step, how step by step you initialize code. So what you actually do, you start from exporting the position of the code, next source root. You compile tools In our case, we didn't compile all of them. We just compiled a setup, which was most important for us for today, which means GenMap, GenBox, and Gmesh to RIA. So one tool for generating the simple box meshes, one tool for producing the connectivity and partitioning information, and one converter. Then we simply copied the case. We created a new map file using the name of the setup and the relative radius to find the unique element vertices. Then we compiled and we ran the case. And with Nek, we generate a metadata file. And that's how this metadata file looks like. It contains a name and the number of files we would like to visualize. And of course, from the log file, we can then extract additional data, which was provided by us and calculated during the simulation after every step or whatever we wanted to do. And in this case, is the difference between the exact solution and the current solution inside Nek. Can we follow to the next example, or are there any more questions? Okay, I don't see more questions, so then I think we can follow to the next example. So, okay, I have to swap here. Fine. So, when visualizing in ParaView, to be honest, I've never used ParaView with Visit. You simply what you should do, you simply should open a metadata file, and at least in Visit is automatic. Philip or Niklas, have you used ParaView?
Yes. So in the recent ParaView 5, 7, and upwards, it should be automatically, if you open that metadata file, it will pick the correct reader. So you don't have to install anything. You don't have to pick anything. Just pick the metadata file and it should work.
Okay, thank you. Any more questions?
Well, maybe one comment regarding ParaView. I mean, it is still the serial reader, right?
That's a good point. I think you're right, actually.
So that means, I mean, for these smaller cases, of course, it doesn't matter. But if you have very big cases, then I guess Visit is the tool of choice. But yeah, I guess you will notice so. If it doesn't work, then it doesn't work, and then you may want to try Visit.
Yeah, but for today, ParaView is fine. There will be no problem today with ParaView. Okay, so can we go forward? So then I wanted to show you a little bit about different use case examples. If you look into there, you will find a number of those under this examples directory. I just wanted to point a few of them. There is this example called Hemi, which is a standard example for the particle tracking stuff. So this one could be interesting to you. If someone wants to see how the linear solver is used in Nek, then you have this linear _ channel to the example. The moving meshes are with an oscillating cylinder example. The other interesting stuff is, for example, smoother. And actually, we will go to this example in a while. The next case is a Taylor QQuet flow. It's a very standard example, once again. Turbulent channel will show you how to do some very simplified, I have to stress it, very simple, to do some very simplified turbulence statistics without using our KTH tools. And there as well, the interesting is this vortex breakdown example which you can find under Vortex directory. All those slides are available on the web page, so I think you can download them later on. So what I would like to ask you to do now is simply to go to the to copy to the run directory the same way like we copied this aduv. That means I this simply cp minus r examples, but this time smoother, because that's one of the interesting, I would say, examples for everybody. It's interesting, first of all, as you can see, because it provides you a possibility to improve the quality of your mesh. The mesh on the left is the initial mesh you have, and the mesh on the right is the mesh after smoothing. And actually, in many cases, changing this is, maybe it doesn't look as a big change, but for the pressure precondition, it actually could be quite critical. So what I would like you to do is just to copy the smoother example and then look into, it's called lpt.user, I guess, and inside this user file. Are you following now? Can I go? Okay, so there are a few interesting things. Actually, I wanted to point you to two places. One is just at the top of your file. You have this C-type include, and then you have experimental mesh smoother.f. This is actually something what I'm not a biggest fan of, but that's one of the way Nek5000 developer assumed that actually someone can add an external code to Nek. Experimental mesh smoother contains a code which will provide a smoothing, those options to your code. And you simply, instead of compiling the code as changing the make file and so on, you simply expand your user file by providing this C-type include. So that's one of the way of doing this, and sometimes in some of the cases you can find it. So I have to warn you that it's not surprising. The other stuff is about morphing the mesh. We were talking about user.2 and user.3. So you can now go down inside the lp.user file to user.2. And as I told you, user.dat is to move the vertices, to deform the mesh, but before all of the grid points are generated. User.2 acts after the grid points are generated. And actually, that's one of the examples of how morphing works. Here, as you can see, a call to mesh smoother is added. Mesh smoother is the routine after mesh smoother.f. And what it performs number of modifications, shifting of the grid points, just to go from the mesh on the left to the mesh on the right. So what we could do as a second test case, I see it takes more time when you go through the internet than usually. So yeah, but what you can do, you can actually repeat a number of steps, elaborate about what the mesh smoother actually does. Oh, that would take a while. So maybe we will leave this question at the end, or maybe during the break. Then I can tell you exactly what it does. But if I will start to go into this detail, I will simply not manage to go through all of the examples. Even now we have like a tight schedule, and so we can go back during the break. So what you could do, you actually could repeat the same steps we did for aduv, meaning after copying, just run genmap, but this time on LPT, just compile, make Nek, LPT, and Nek BMPI. So This would allow you to run LPT case. I could do the same. However, I see that we are like 20 minutes left for this session, so I will try to speed it up a little bit to get to the main example. But what you will see, you will let's say you will not get much output of the run. Simply in the log file, you will have the section that will show you the information about that smoothing is performed, but you will not get information what was the mesh before and what was the mesh after. So now what we could do, we could start to do our first code manipulation, code modification, and simply add to mesh smoother to this routine user that the call to the routine that would allow us to outpost to the directory the plot file before the mesh was smoothed and after. And of course, there is in the documentation of Nek a nice description of different various frequently used routines. So you can go into the Nek documentation to see what really the routine does. And this routine that allows us to write output, the plot file is the outpost routine. So the modification which we will do is simply adding before the mesh smoother the call to outpost, and at the outpost as the argument list takes the velocity component Vx, dy, Vz, pressure, and temperature, and the last part is the 3 letters starting the name of our new file. You could leave this as 3 empty spaces, and then you will simply not change the name of the simulation. But what's important here is as well that those Vx, Vy, Vz, you have no access inside user.dat unless you will add our global memory description, which in this case is include total. Total is the include file that combines inside many different include files like the size, solution, parallel, and so on and so on. So in this single include allows you to gain access to the more or less all necessary variables. On the other hand, total is kind of dangerous because it loads a lot of different variables, and you have little control of this. And that is why in most of my cases, I usually try to avoid total and rather to use a specific include file. So after adding this outpost before and after the mesh smoother, you could recompile the code, rerun the code, and then what you would get, you would find 2 files, which would start with mesh LPT1 and mesh LPT2, and renaming, let's say modifying the LPT, this LPT underscore Nek5000, which you could generate using the VisNek, and simply adding LPT in MSH in the front of your name, you could visualize that. I think we have to go to the next example because we are left only with 20 minutes. So I would say you can try to test it at home later on, or we can during the break, or we can talk about this later. But now I would ask you to go to the example and to uncompress the file which you downloaded from the course webpage. So this will be, we can go up and up and up. So I have here as well this workshop example. We can go to the workshop example, and there is an example called Excel Gmesh. So this is flow past cylinder, cylinder 2D example, which contains all Gmesh part. That means we generate the mesh from scratch. It contains source code and as well a run directory. So under Gmesh, you have a bash script that allows to execute Gmesh, in my case, Gmesh 4.8, and then you have the actual geometry file. I'm not sure how well you know Gmesh. I'm not going to give you now the introduction to, let's say, the full description of Gmesh. It will be just a very short introduction, but that will allow you to make a next example, if we will manage, because I see time is flying quickly. Under run directory, what you have runtime parameters, this par.par file, and as well a set of history points. A set of history points is simply, in this case, is this excel.his, is the first line contains the number of points, and then we have x and y coordinates. Those are the points where after every time we call a history points routine, the value of the velocity and pressure will be calculated with the spectral accuracy. That means we will have as exact value of the field in that position, irrespective whether it's the grid point or it's outside the grid point. And then there will be, this file will be appended with all those values. And then we have source directory. And then we have the compile script, user file, and the size file. So we actually have already everything what is necessary to compile. So we go to source, and let's look what the compile is actually. So I always were talking a little about this script. It's a very simple script that collects all of the variables we have to provide. That means where the code is located. I hope that's correct. I will have to check if that's corrected. What's the Fortran compiler, C compiler? There is no specific preprocessing flags. There is no additional files to be compiled. And then I have two arguments, clean and all. And that's everything what's there. So I will simply check if really my path to Nek is correct. No, I need one more. So what I have to do, vi compile script, I have to add one more layer. And now I can simply do compile. First, let's clean the code. That means compile script -- clean. And then you get the question, do we have to clean a third-party libraries? That would be QQT library, that means gslib, that will be BLAS, that could be possibly Hyper, Parmetes, or whatever. In this case, we say no, we can keep them the way they are. And then we simply run compile script -- all. And that allows us to compile the code. So that's part related to the compilation. But what about the mesh generation? The mesh generation is done by, in my case, I'm using this Gmesh 4.8 by running the script and executing the file with the ending with .geo. So going very briefly through Gmesh and through all this kind of stuff, I will not add here a full description, but Gmesh has actually a pretty nice scripting language, which allows you to add multiple different variables, like here. This is useful if you want to run a scripting, you want to script your mesh, but at the same time you would like to experiment a little bit in the interactive mode. It provides you possibility to work on the objects like points, lines, curves, circles. You see here, I have here some point sections. I have here some curve sections, and as well I have the surfaces. And it has some ability to operate it on those sections. So what I'm doing in this part of the script, I've started with defining some parameters in my script and even building this interactive menu to change them interactively during my work, interactive work. Then what I did, I defined a point in the center of my cylinder, and then I defined 1/4 of the region surrounding cylinder. That means one of the small region close to the cylinder was defined as my surface. I defined this by giving points and as well lines and circles. I combined this into the surface, and after that I started to replicate and rotate this to start to fill in a whole domain. We have not much time to go into all the details. No, I don't think so, because Nek internally, the question is whether Nek has directly a utility to work on this STI objects. I don't think so. This you have to do through the meshing. You have to mesh it. This, like inside Nek, inside Gmesh. Gmesh has some ability. The drawback is that you have to go from any triangular mesh to the hex meshes, which can be kind of okay in 2D with Gmesh. In 3D, it's more problematic. It is not simple part of the whole workflow. So there is no just black box. You put it in and you get output. It doesn't work this way. Okay, continuing the stuff related to the script. After I generate my whole mesh, I start to define the physical properties. So first of all, I have to provide a surface physical properties, and that was when I was doing the script the first time. I forgotten about this, that all the volumes or surfaces where my fluid resists, let's say through which the fluid goes through, the flow is taking place, they have to be defined as a physical surface. Otherwise, they will not show up in the mesh. So it's not only to define the borders, like in my case, I have the wall on the cylinder, I have an inflow on left, I have the outflow on the right, and I have a periodic boundary on the bottom and on the top. I have as well add the physical properties to the whole, all parts of the domain where the flow would go. And then, of course, I define the boundary conditions for each of the external boundaries of my domain. And at the end, I have to say, because at that point, what I did, I simply generated the set of objects like lines, which are in my case boundaries, and surfaces, which are the part of the domain, but they are not splitted into the smaller parts, which are at the end will become my elements. So what I do this with transfinite, and I'm taking every single line, I specify how many cells should be splitted this line, and what is the progression radio. With the progression one, I have the uniform mesh. With the different version here, different values, I will have some geometrical increasing or decreasing size of the splittings. And what is probably important is to see that all those lines which I have in my list and which I generated somewhere here in my curve section, and later on as well, all those lines are oriented. That means they have the beginning and at the end. So sometimes, like in the last transfinite curve line, you see that some of them have a negative sign in the front, which simply means that I change the order because they have the beginning at the end, and that's what you have to be careful. After splitting all the lines, I can start to split all the surfaces, but this way it's not the automatic meshing inside Gmesh. That's what you have to know, understand. I finally, to get a hex split, I do this manually, and that's a drawback. And the reason is why I'm doing this manually is that actually Gmesh provides a recombination algorithm for 2D domains, but then there is no way of doing this in the proper way in 3D. So that is why I'm doing this even in 2D in the manual way, because at the end, if you do the 3D case, you have to do this manually. And actually meshing is one of the most problematic, I would say, part and time-consuming part here. And at the end, I have the last section of my script, where I simply provide the final meshing and write them in the proper format to the disk. So the outcome is something what you see on the right. So this is a splitting into the elements, the initial splitting into the elements we have in this case. So what I and to simplify everything, in my case, so under source we have already Nek5000, so I can do cp Nek5000 to run. That's what we've already got. We compiled the code. Then we can go to the Gmesh, and here we have the make mesh script, which allows us to execute, and that's a kind of production runs which I do. If you put into the Gmesh the minus at the end, it will not start interactive mode. So you can do this in to some extent in parallel at the end. So what I can do, it's simply Gmesh. Oh no, it's different code. It's not my laptop any longer. Gmesh. Let's see what will. Oh no, okay. It worked nice. You cannot see the result because it showed on my different screen. So my output looks this way. So everything is meshed properly. And I've got a new mesh file. But what we have to do now is actually convert the mesh file into the Nek format. So what do we have to do? We have to run a converter, which is under Nek5000 bean, and it's called Gmesh to Nek. And what we have here, I'm running this. So the first stuff it asks is, what is the dimension of my mesh? I have two-dimensional mesh, so it's 2. Then it asks me about the name of the file containing the mesh, ext_sil. And then it actually lists all of the boundary conditions which I have inside my mesh. So I know that my number 2 was wall, my number 3 was inflow, number 4 was outflow, and perturbation bottom and perturbation top were 6 and 5. And actually, the next question is how many periodic boundary surface pairs I have. I have 1. I have the periodicity between bottom and top, which means I have, and this is my 6 and 5. So I have 1 pair of periodic boundary conditions. Then it asks me what numbers of those periodic boundary conditions is. And because I go from the bottom, which is 6, to the top, which is 5, so I give 6 and 5. And then there is the question about the translation vectors between 6 and 5. And I know that I didn't move anything in x, so it's 0. I moved the width of my domain is 30 units. So it's 30. And there was no motion in Z. Actually, Z doesn't exist. So that's my translation vector. And now it produced a RIA file, actually RE2, which is a binary file, which contains the Nek format with the mesh. So what we can do, we can copy this xsil RE2, which is our Nek format mesh, to our run directory. And I go to the run directory. So what I here have, I have the code, I have the mesh file, I have runtime parameter, I have the history file. What is missing here is actually the connectivity information and partitioning information. So what I have to do, I have to generate a map file based on the RE2 file. That means the file containing the mesh information. So I'm running this by, once again, going to Nek, bin, genmap. Then I'm providing the information. What is the name of the file? And what is my relative radius of the mesh? And the result of this is actually the map file, which contains the connectivity information as well as the partitioning. And at this point, we are ready to run the code. We have the code, we have the parameters, and then we have the connectivity information. So what we do here, we simply run, once again, Nek binary running script, which means Nek PMPI, then the name of the setup and number of processors to run it on. The result is as we can see, the code was, because it was just 100 steps, so it was just a very short run. We've got 6 different plot files, so we can run, once again, visnek, and visnek generated xsil.nek5000. So that's the file which can directly open in ParaView or in Visit. It's already 2 o'clock, and unfortunately, I haven't finished yet the presentation. This we covered. So the important things, maybe just 2 more minutes to go through this, because we covered already this part related to the conversion using Gmesh to Nek from Gmesh, where we give all of those parameters to Nek. And then we talked about compilation. But now, what is specific about running Nek with Gmesh and with any other, because it will be not only a mesh related to the Gmesh, any other mesher which is not internal Nek mesher has a very specific stuff. It does not, the mesh file does not contain a proper boundary condition description that would be found in the RE2 or RIA files generated by Genbox, Pretec, Prenek, whatever that would be the Nek native tool. So what we have to do, we have to provide inside a subroutine user dat, we have to provide a conversion. And you see that when we looked into that previously, we saw that inside Gmesh, and that was done inside, we can go back to the script. It's here that we called the physical properties. Wall was 2, physical inflow 3, outflow 4. The same numbers showed up during the conversion. It's here that we have all the boundary conditions that are mentioned. And then those boundary conditions actually has to show up inside user.dat, where we simply use the routine, which is called set boundary condition. And to each number, we provide a character string containing from the 3 characters, which define in the proper way the Nek5000 boundary condition. So that is why 2 is wall, 3 is inflow, which means Dirichlet boundary conditions, and O is 4, which is stands for the standard outflow. I as well have a smoother in this case, and you see that I'm using, first of all, I have this include experimental mesh smoother, and then inside user.to, I perform smoothing as well as I'm outposting those data, so I can see how the smoothing actually acted here. And then we could talk a little bit about user check, and that would be a closing part here. So as you can see, inside user check, we perform number of operations. Actually, this is our main place to act. Some of the operations are done during initialization step only, that I have this if I step equal to 0, that will be only initialization. The rest will be done during the time loop. So what I do during the initialization, Nek5000 provides the possibility to define objects, which in 2D will be a surface, that means 1D surface, some curves. In 3D will be 2D surfaces. And those boundaries, external boundaries, can be used to calculate some integral values like drag, lift, and so on. So what I'm doing here, actually, I'm taking a boundary conditions, which in my previous, when you look into the user.dat, we did set boundary condition 2 to be wall. Here I'm taking the same boundary conditions, and based on these boundary conditions on this wall, I use a routine called create object to generate inside Nek information that it has to calculate drag, torque, whatever the value it will be calculated, and then integrate over this object and outpost this to my to all the torques to my log file. So during the initialization, I generate the object, and during my call, during the time loop, every number of steps, you see here, I have some mod iStep IO output. There is some every number of step. I call torque calculation, and this torque will be calculated on the object which I define during my initialization. And I think we will have to stop it here, even though there are a few more things to talk about. There is as well a directory lead-driven cavity, which I hoped to could be able to go through and make. You would be able to make your own test case, but I see I didn't manage because it's already 2:06. I'm afraid this was pretty quick. Are there any questions? Does it mean it was too fast and it was too difficult to follow? Yes, you can find the course files as well. I have a solution to this exercise. They are on the web page. Everything is on the web page. Oh no, I don't have a web page here, except the solution. Yeah. Unfortunately, Nek is not a simple code. In that case, I tried to do this step by step. Yeah, let's say yeah, you can have the time-dependent boundary condition. User BC is the routine which is called during every time step. So if you will have the time-dependent boundary there defined there, then they are time-dependent. Oh, what do you like, sinusoidal inlets or something like having an edge as an inlet for same time and the outlet? Okay, changing inlet and outlet I never tried, and I'm not sure it would work. Philip, had you or I mean?
Yeah. An edge as inlet for some time and the outlet for. You mean changing dynamically whether it's inflow or outflow? Well, as long as it's Dirichlet, I mean that would work. But changing the letter, I mean,
see, it's not so simple because you have masks.
Yeah, exactly. Then you have to I would say
stuff.
Yeah, then you have to restart the solver if you want to change the type. So, for instance, going from Dirichlet to stress-free or something. I mean, you had to do a lot of initialization again, which is maybe easier just to restart. But
yeah, everything has to be reinitialized because the boundary condition influences the pressure preconditioner. So the whole pressure preconditioner would need to be restarted as well.
Yeah, but if it's only about having Dirichlet conditions, which at some point are positive and some point are negative, perhaps, or that you change the type in a sense that maybe the pressure is higher inside than outside, and then at some point it changes. This, of course, would work. But I mean, is there a specific case that you were thinking about? Well, maybe now the question would be, Adam has prepared an exercise, which is the one that you have here. And the original idea would have been that you have a few minutes time, I mean, a few minutes, maybe 20 minutes or so, that you could try to work on this yourself, trying to see whether it works for you or not. I guess the question would be, would be whether you would like to do that now, so that Adam could present the exercise so that he can work on that afterwards, or whether we should just make a break now, and then the next step would be to introduce the framework that we have for turbulence simulations.
Yeah, the question is as well, because even this example was relatively difficult. Is the framework statistics not too difficult right now?
I mean, I would say it would be good maybe that you would have that it would take 20 minutes or so trying to work on this example case, because that's then when you would see whether there are problems or not, and afterwards we can then continue with the lectures. Does it sound okay? And maybe one answer to the question regarding the recordings. Yes, I mean, I'm recording, and I will put it online afterwards once this is done. So yes, you will get the recordings. Okay,
one solution, because we are limited in time and we are already quarter past. One solution could be to go with the presentation about the framework and to split a second hands-on session into two parts, shorten the framework hands-on part, and to do the lead-driven cavity example during the second hands-on session in the beginning of it. would it be okay? Philip, what do you think?
To me, either way is fine. I mean, we can also now continue with the lecture and then just round off the day with the hands-on, which is then both for the lid-driven cavity and the framework. Maybe
Okay,
that is the best.
I think actually that probably would be better.
Yes,
So
but
let's
anyway,
take 5-minute break.
Let's take 5-minute breaks. Break. Now it's 13 past. Let's continue at 20 past. That's in 7 minutes.
Okay, 20 past. We start with the information about the framework.
Yes.
And then we will go with the second hands-on session, starting with the lid-driven cavity.
Yeah.
When everybody could really write its own. I will explain once again a little bit how should it be done. Then we can as well show the solution to that, which is not posted on the web page yet, but we can add the solution as well to this. And then we can follow the hands-on session with the framework at the end.
Yes, I think this sounds good. Okay, let's meet back at 20 past. Thanks.
Okay, so now we went through all the basic stuff inside NAC. So we go to more advanced stuff, how we can really do some more complex simulations. And there are actually multiple different ways of doing this, and there is many different things you can do. As you probably already noticed, Nek5000 is not the black box, it's more like a university code, when you actually have to know a little bit what is inside. But as long as you know what is inside, you can do many different things, like linear stability analysis, or statistics, or you can add some very specific inflow conditions, like the synthetic eddy methods, or many different things. So for a long time in NAC community, the way of adding those tools was done through the examples, but we've learned that it has some limitations, and that is why we at some point thought that maybe it would be better to produce a kind of general framework when it would be easy to add some tools. And today I will talk very shortly about what we've done. It's not full, I would say, it's open source code, but it's not, let's say it's not stored in the Nek5000 repository at GitHub. We have our own, so I will shortly talk about what it is and how to use it. So first of all, it was simply a set of routine that we wanted to make as a background for adding very multiple tools, because one of the problems which we encountered before, when we were simply using different examples as a way of spreading code, we found that then you usually get into a problem when you have to combine multiple different tools, and then different people combine them and put them together in different way. So our idea was to do something what would allow you to easily combine multiple different parts of the code written by different people, put them kind of easy, maybe not the easiest way, but kind of easy way together. But at the same time, we didn't want to go into NAC core code. We wanted to operate through the existing interface. That means mostly going through user check. That's the place where our tools work in most of the cases, or rather almost 100% of the time. We don't change the NAC code. And then as well, we follow a Nek5000 philosophy. That means we try to be as similar to the NAC code as it's possible. And as well, we wanted to have kind of the easy documentation that would allow to look into the code, and as well allow us to look into the NAC code as well. So that is why we decided to built around this the oxygen documentation, which is available online. Actually, online you can see the whole, almost whole Nek code. The problem is that the oxygen does not allow you to visualize include files, which are unfortunately an important part of Fortran 77 and Nek. So what actually is a structure of our framework? Its main part is actually a toolbox, which divides into many different sections, like a driver, which simply contains the most important part. Those are the parts which are always included into the code when you have to use our framework. And that is like the monitoring tool, the runtime parameters reader, and so on. Then we have some more specific parts which can be included or excluded from the compilation. So, for example, you would like to have some time stepping. You would like to know the spectra or the stability. You could use all the RPAC, or you could use the power iteration. So you could use them together, or you could split them. Sometimes, of course, you cannot use them together. You cannot use Arnoldi and power iteration at the same time. But you can, for example, combine different parts, like the checkpointing can be combined with base load calculation for SFD, or with the statistics calculation. So you can, the idea was to have a number of different tools, which we call modules, and then to combine them. Some of those modules can depend on each other. For example, statistics can depend on the meshing utility, which is called map2d. And we tried to put it, and you can find everything on GitHub. There is no tarbile in this case. Everything is available through Git repositories. And then you can see that on our local KTH Nek5000 repository, that's the web page, there are three main repositories that are pinned. Is the KTH framework, KTH examples, and KTH toolbox. Toolbox is exactly the structure which I showed you. That means it contains different pieces of the code, and then you can combine them together. Examples actually shows most of the tools, or almost every of the tool, has its own example, which explains how to use it. On the other hand, framework is the repository that combines three different repositories. That means through submodules, it combines toolbox, examples, as well as Nek5000. We include here a given commit inside Nek5000 because we want to be able to provide a fully consistent set of tools to be 100% sure that this will work with the given release of Nek. In this case, it's not even given a release, it's even a commit, because something was corrected meanwhile, and we wanted to have the code that has this correction, because one of the tools depend on this correction. That is why the one framework actually is the way to have a complete set of code that should work together. At the same time, we have the oxygen documentation, and here on the right you see the link to this. It's simply GH pages on GitHub, and this is built through the oxygen, and that's part of our web page. This is the documentation. We tried to write the documentation which would be as complete as it's possible, but as usual, there is lack of time. Like in Nek case, not everything is up to date. But here is, for example, description how to get the whole code. And the best way to be 100% sure that the framework would work is to clone from Git recursively all of the framework together with its submodules. So in one clone, you will get all of those stuff: examples, Nek code, and toolbox. So how it's supposed to work? Our assumption was that everything goes actually through user check. That means there is no other calls outside user check. And that's how it works. Of course, there can be some exceptions, because if you, for example, are calculating spudge, or you want to calculate the steady state with forcing, then you have to, inside user F, provide a value of the forcing. However, at this point, it will be just reading from the array and place it in the proper position inside Nek, but the whole forcing will be calculated inside user check. So there we have a few standard steps. First of all, we have to initialize our framework, and that's done during the initialization step. So we have this if I step equals 0, and then we call framework start. Then we have the monitoring part, because framework provides additional features. Nek5000 version 19 doesn't provide, for example, a wall clock time for your simulation. You have to know how many steps you can do during the, for example, on Beskov, we have to run within 24 hours. So you have to calculate approximately how much time you will spend. Our framework provided additional tool which allows you to measure the wall clock time, and then you can you don't have to calculate and approximate any longer. And that's what's done inside frame monitoring. Then you have a space for some additional tools. In this case, it's statistics, stat averaging. So that was the example using the statistics. And then you have the finalization of the framework, everything inside user check. Of course, there are some additional routines, additional interfaces that the framework assumes. And this depends on the tool you use. The framework itself requires three different routines. Registration, where you simply tell to the framework which kind of tools you actually use in given case. Here we, for example, registered statistics. And then you have the initialization, where you say which tools actually will be initialized, and some of the tools actually have as well a finalization routine. Why there are two different routines for registration and for initialization? The reason is simple, because different tools within our toolbox can be dependent on the other tools. And we let first register, that means to tell to the framework what tools are we going to use. Then framework tries to figure out if every dependencies are correctly filled in. If they are not, it will say, okay, something is missing. And if everything is correct and all the dependency between different tools are actually fulfilled, then it can start to read runtime parameters and to initialize all the tools. So simply because framework itself tried to find the dependency between tools, that is why we have two different steps, registration and initialization. So one of the important part which we had to do when it comes to the using specific tools and to avoid conflicts between those tools is adding a space for different runtime parameters. And this is actually a feature of Nek5000 which we asked for and which was added, meaning that, as we told in the par file, you can have different sections. However, Nek5000 checks the sections. So if you will add the section, the new section that it's not known to the code, then the code would crash. However, there is new possibility that every section starting with underscore will be actually not checked. And those are the user section, and we use this feature. So each of our tool, or most of our tool, because not all of the tool requires the runtime parameters, will provide its own section with the runtime parameters, and this section will always start with the underscore. And this way, you simply let the code not to information that this is actually the correct section, and Nek5000 will not crash because of that. The list of all of the runtime parameter added by different section is actually added to our documentation, and it's done in two ways. You have a list of all of the modules and the runtime parameters only, and then you have description of every of the tool, which because the Oxygen uses name module, we call the tools modules. Then you will have every tool will have its own description of the runtime parameters. And that's why each of the modules, that means those tools, will provide some interfaces, some subroutines that performs given steps. And then the documentation as well contain the list of all the possible interfaces inside our toolbox. Once again, I have to unfortunately say that not everything is up to date. The work is ongoing, but yeah, we try to fill all the gaps. Most of the tools which are very often used are actually documented, so they have whole information. So what are our modules? There's a number of toolboxes, and then you can see that driver, communication, frame, checkpointing, post-processing tools for the statistics, and so on and so on. There is a number of different tools, and there is a module page in our documentation which allows you to go through all of them and to see each of the tools separately. So when you look into the documentation of given toolbox, here is, for example, checkpointing. You can see some short description and some long description inside. You will have the information what files are actually building a given tool. As well, you will have the information about what are the interfaces, that means the routines you can use, and on the web page, you will have an example, actually, how you should configure your user check and all those frame underscore user register, frame underscore user init, frame underscore user end to be able to use this given tool. So here once again, we have the framework start, frame monitor, frame end, which is a standard part of the frame. You cannot run it without those routines. And then you have checkpointing routine somewhere inside. And of course, here one could ask a question, okay, why we added a checkpointing routine? Because Nek actually has a checkpointing possibility. And the reason for us to have actually our own checkpointing routine is the fact that Nek is a multi-step code. So it can be second or the third order depending on the configuration. And that means that you always need 2 or 3 last steps to perform the clean simulation. However, the native way of restarting Nek5000 will produce only a single file for restart. This is, of course, very, very useful because at the given step, you can simply stop your simulation, write a plot file, and then you can start from that plot file. However, then you have to be aware that the first 3 steps of your simulations after restart are not exact because you slowly increase, let's say slowly, you step by step increase the time integration order. From the first Euler step, then the second step will have the second order, and the third step will be the third order. So you simply slowly increase it. And in most cases, it doesn't matter because it's the noise which you include in the case is not enough to start like instability. But we found a case which was a pretty nasty and sensitive jet in the Crespo, where actually this was breaking the whole simulation, and actually it was not possible to perform the simulation. And that is why we, for example, have a full time restart procedure, our checkpointing, which actually keeps the order of time integration during all of the simulation after the restart as well. The next part of the description of every single tool is, of course, a description of all of the runtime parameters, as well example of how the section inside the par file should look like. For example, the checkpoint, you have the interval for the checkpointing, you have whether you really restart from the given checkpoint, and as well about which checkpoint set files, because this is a multi-step method. That means you will have a set of files consisting of from 2 or 3 files, because depending on whether it's the second or third order time integration, and then you will have to choose which set of the files you will use. And of course, after that, because it's deoxygen, then you can actually go directly to the code and see the code line by line, except of course include files, because include files cannot be added to the oxygen. At the same time, we provide a possibility to look, like here we look into the, it's the web page where you look into all of the routines. So you see directly the code, and the blue lines are the links, so you don't have to grab through the code to define the other routine. You simply click on it, and then you see the other one. But we, at the same time, decided to provide the deoxygen documentation, not only of our toolbox, but of all the Nek5000 code. So after going on this, on the left panel to the file list, you can see all the files except the include files that are actually part of Nek5000 itself, and you can actually browse the code, and that's actually a pretty nice and good way if you have to develop somewhere and learn to what the code does internally. And of course, the description, the detailed description for each of the use case can differ, can be, sometimes it's unfortunately outdated, but that's, for example, the case, the description of the checkpointing module, which tells you that depending on what kind of routine you will, let's say what kind of simulation you will do, whether it will be DNS, you will have the RS restart file, whether it will be like perturbation, that means linear mode, you will have additional RP files and so on. And then it's the whole description that you have 2 sets of files and blah, 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 which allows you to use this code. So when it comes to the repositories, going back, because we are talking about the documentation, there are 3 those repositories, Nek5000, which we point to the given part of the code, the given version of the Nek code, which is supposed to work with the toolbox. Then we have the toolbox itself. I will not go into the structure of that because it's not so important for you. For you, it's important is that there is a shell script, which is toolbox_path, which will be used later on when we will talk how to use our toolbox itself. This toolbox path is a script which provides all of the paths which are used inside toolbox and that allow to properly compile and link the code at the compilation stage. And then, of course, we have examples. Once again, all the examples, this is the way how to learn how the toolbox works, what are the different possibilities, what are the different actual tools. And you see here, for example, there is this Arnoldi linear stability, there is DNS run, there is a linear simulation case, there is an example with the power iteration mode, some fast, SFD, that means sequential frequency dumping to get the base flow, some tripping tools, some history points, and statistics. Later on, we will see whether we'll manage to talk about the examples. I would like to show you 2 examples. One will be this external cylinder DNS. It's like similar to what we were doing, but this time using the toolbox, like a checkpoint restart. Then I thought maybe we would, if we would have time, we can look a little bit deeper into the statistics example, which actually consists of two stages of the collecting statistics. That means here it's this periodic Hill statistics. That's what that collects all of the parts, and then it's the post-processing part, periodic Hill post-processing statistics 2D. So there is as well on the webpage information what are the different parts of the every example. So you have that information that every example consists, of course, all the files which are required to compile, which is the user file containing all of these interfaces like user check, user BC, user F, and so on, a size file, a compilation scripts, which could, in some cases, require some adjustment. But if you clone all the framework, not each of the repositories separately, then everything should work directly without any changes. Then you will have to add the makefile underscore user.inc. We use in our framework a way of adding external code through the modification of the makefile. So we don't use this simplified way by using the C type include, simply because we have too many files to be added. That would make a user file really a number of thousands of lines, and actually that is not very useful. And then you have all the other necessary files like the runtime parameter, some information about the box, possible RE2, or some cases. There could be some examples which don't have the mesh, for example. All of the, and this is the example can be all of the external cylinder cases. There's only DNS that contains the mesh. The rest do not contain it because actually it's the same mesh, so it's just a copy of the file. And then, of course, there is information how to compile. In most cases, it should be straightforward that you simply compile the code running the compile script, and then you can execute code directly. Of course, after creating the map file, after getting sure that the mesh is in the MEC format, and so on and so on. So when you actually do your own case, the important part is really to generate a proper compile script, to generate a proper makefile underscore user, and to generate a proper user check. In some cases, there can be some additional interfaces required. Like in the case of statistics tool, you'll have to provide as well an interface that would say that you will tell the code how you actually doing where is your span-wise direction in the mesh in your domain, and how you're supposed to perform the span-wise averaging. In the case if you go from the 3D dimensional to the 2D span-wise averaged. So then it will be additional routine that will be required. However, that will be described in the documentation. And of course, when you start to collect information, collect the statistics information, you will have to provide additional routine which will calculate the derivatives, maybe some rotations and some stuff. So those are the additional steps. And of course, there is as well in the documentation, this time not in the Deoxygen, but in the inside repository itself. So you will see the list of all of the examples and the very short description of all of them. So that's the end of the presentation. And actually at that point, we could directly go to our Nek5000 repository. And it's pretty easy to find because it's enough to Google KTH Nek5000, and Yeah, and that's this one. And we are on our web page. So as I said, 3 repositories, toolbox and examples. However, framework simply takes everything together. We have as well our documentation. And here, okay, now it will be a problem because I'm sharing the screen at the same time. So now we already went through this. You could see that there is information how to clone our framework. There is a list of interfaces under runtime parameters. There is a list of parameters, and so no, this is not here. This is here. And actually here already you see that, for example, Arnoldi is not, the documentation is not updated yet because it's not a table. And then of course you can go to the modules. We can look into any of the modules, like for example, statistics. It has its information, list of the subroutines, description, what it does, what it collects, what is the output, how we're supposed to use it. There is the documentation about how the code look like. And now here you see there are additional interfaces required, like user statistics trans v, where you actually provide the vectors you would like to do, and as well like this user map to the get, where you simply say, what does it mean? What is the span-wise direction in your case? And this is followed by the runtime parameter example of the section, and simply each of the subroutine can be found directly in the browser. And at the same time, when we look again to our left side, you have a menu, you have files, and you have as well Nek5000 under this. Under Nek5000, you have a core, and we, for example, can go directly to see how the initialization look like inside Nek. We have inside drive 1.f, Nek init. We can have a caller graph and a call graph, which sometimes are useful, sometimes not, but we can have as well look directly into the code. So actually that's one of the good ways and easy ways of learning. I'm not sure how much you are familiar with this, the kind of the oxygen documentation, but if you want to see what the geom reset is, you can go directly to the code and you can see what geom reset does. So that would be, that would be the end of this part, except we will go into examples again. So you can see all of the examples. You see the description of the examples, what they contain, how to compile them, and then the list of all of the different examples, like generalized synthetic eddy method, statistics point in the binary format, tripping line, post-processing statistics, and you see that there are like pipe statistics or periodic yield statistics. There are different type of those simulation because they are slightly different. And actually you can go and you can actually see each of those cases. But you have the mesh here in the binary file actually. Then you have the compiled script, make file, and all the user files and so on. So actually we could stop here, I guess. What you could do before the next session, hands-on session, you could go to our documentation. That means you simply grab for KTH Nek5000. You go to framework, and then you have this documentation on the right. You can open this link, And on the first page, you will have information how to clone. So I would suggest to clone the whole framework is just to copy paste, and then what everybody can do. Actually, I already cloned this, so I will remove -f kth framework -rf, and I will clone it. And this will clone all 3 repositories. It will take a while because yeah, cloning will as well take information about the GH pages. Now it's cloning examples. And now we are ready. We can go this kth framework. And here you have 4 directories, actually. You have Nek5000, which contains a whole code. We don't need anything more than this. Toolbox, examples, and and as well documentation. You can generate local documentation for Nek5000 if you would like. It's simply to run the oxygen documents, the oxy file, and then it will generate local. Oh, now it can crash because I didn't generate HTML subdirectory actually, or it will produce, I don't know, not sure. But that's, you can actually produce local all this documentation and have it there. Okay, I think we can stop here. And then it would be like 15 minutes break. And okay, I see that someone has a problem with Zoom, and we have to admit very often a person. So, but first of all, are there any questions? Okay, I don't see any questions in the chat. So then that means we could break here 15 minutes. And after the break, I will slowly try to go. Let's try to go through the examples of this cylinder case, and let's do this case with the flow with the lead-driven cavity. And then after that, we can go to the framework.
Yes, yeah, I think that's very good. But then let's have the break now until 1/4 because now it's exactly 3 o'clock. Let's continue at 1/4. Okay. And of course, you can post questions also during that time, of course.